All right, well, hopefully today will make sense and you'll feel comfortable with it all, and your confidence will be brimming by the end of the day. Okay, so we're still in chapter 10. We started talking about VSEPR. We're going to do more VSEPR, and then we'll talk about molecular polarity, dipole moments, and molecules. And then we'll talk about valence bond theory. We may not get to MO theory today, but that's not manageable. Okay, so I think we did these structures last time, right? PCl5, dichloromethane, nitrate ion. We drew VSEPR sketches for those. Let's do some more. SF4. Okay, so the goal should be to look at a structure, or look at a formula, excuse me. Look at a formula, come up with the Lewis structure, and then from there come up with the VSEPR sketch based on that table I gave you last time, and then ultimately come up with the valence bond sketch later on. Okay, that's down the road. All right, so SF4. Okay, so SF4. What atom would go in the center? Just, quick review of the. So usually the higher electronegativity atoms go on the outside. So we're going to have this Lewis structure where you've got the fluorine atoms on the outer positions, and then we put lone pairs on all of them. Okay, grand total. Well, this is a covalent compound, so everything's going to be together. You've got 28 electrons from the fluorine atoms and another 6 from the sulfur. So 28 plus 6 gives you 34 total electrons. How many have we assigned so far in this? We've assigned 32 so far. So at this point, we end up having to put a lone pair on the sulfur. So what is? Looks like I put my dots. So this is the Lewis structure. What does the VSEPR sketch look like? So this is a steric number of what? Yeah, steric number 5, right? So I got 4 bonded atoms, which are the fluorines, and I have 1 lone pair on the sulfur. And that gives me a steric number 5. So the electron geometry is the trigonal bipyramid. What is the shape? Molecular shape.
C-cell.
That's going to be a C-cell. So what is the VSEPR sketch going to look like? How do we get there? Well, so here's what I want you to take away from VSEPR. We have 5 generic shapes for the electron geometries. Those are on your table. You don't need to memorize how to draw a seesaw shape if you know how to draw the generic trigonal bipyramid. So let's start with drawing a trigonal bipyramid, and we'll go from there. So if we had, let's just say if it was 5 fluorines on this. What if we had 5 fluorines on it, but we don't? Okay. So where do we take that fluorine off to put the lone pair on? All right. So just to rehash your memory from yesterday, do you remember where the lone pairs go on a trigonal bipyramid? Do they go on the axial positions, or do they go on the equatorial positions? All right. So these are the equatorial positions here. Okay, and then the axial positions are the axis of the molecule where the equatorial positions can spin around. So do we take off this fluorine to put the lone pair on here? Or do we take off this one at the bottom? Or do we take off one of these three? One of those three, right? One of the equatorial positions. Does it matter which one I take off? The answer is no, it doesn't. Okay. But for the sake of drawing what could possibly look like a seesaw shape, I'm going to go ahead and take off this guy. And there's my VSEPR sketch. Okay, now if you want to really hurt your neck, I don't want you to hurt your neck, but if you really want to have an interesting, like tweak your neck, I don't know. But just tilt your head this way, and it'll look like a seesaw on two legs. All right, and so that's this molecule with a equatorial. So here's my seesaw shape now. I took off one of the equatorials. If I turned it on its side, I would have a seesaw shape. Right.
So the fluorine has to be directly at the bottom then?
Yeah. So this is the original trigonal bipyramid. Right. This is just a full-on trigonal bipyramid. This would be like PCl5 when we did yesterday. Okay, and then the rule is that in order to minimize electron-electron repulsions between neighboring groups, you got to take off one of these equatorial positions when you have a lone pair. Okay, so now there's a lone pair here, taking out all this space, and it's repelling these bonds kind of more this way. Okay, lone pairs, that of all the electron groups, lone pairs take up the most space. So do you need to memorize this structure? No. You just need to memorize the generic trigonal bipyramid and then take off lone pairs accordingly, based on that rule. All right, so I've had students think, oh, I got to memorize, 15 different shapes. No, just memorize the 5 originals, okay, and then take off lone pairs based on your knowledge of VSEPR. Okay. So what do you think? Not too bad? Yeah. That's a good question, and the answer is you don't have to draw the lone pairs. Sometimes you'll see people draw a lone pair in here, but here's the thing, the molecular shape, unlike the electron geometry, okay, the shape just shows what the atoms are doing, not what the lone pair is doing. So when you draw the shape of a molecule, you leave out the lone pairs. Okay. So even though you don't see the lone pair there, it's there.
Would you mark as incorrect if you did?
I would not, right? I mean, if you did this, if you went like this, you say, yeah, there's a big lone pair out here now. Okay, I said, okay, at least they know there's a lone pair there, right? That's the concept. Okay, just understand that that when you're talking about the shape of a molecule, the molecular shape, you're just talking about what the atoms are doing, right? That's what you're talking about. Whereas with the electron geometry, it's still a trigonal bipyramid electron geometry. Right? It still has this lone pair there. It still has a steric number of 5, right? 4 bonded atoms, 1 lone pair. Right? Still steric number of 5. All right. Anything else? All right. Let's do some more. How about I3 minus? Okay, this one's going to be a little interesting. All right, so here's I3 minus. If we were to draw the Lewis structure for this, it's just going to be 3 iodine atoms in a row. All right, so that's the basic framework. Grand total, I think we've got, let's see, 22 electrons, valence electrons total, right? So you get this basic framework, you add the lone pairs to the outer atoms first, that takes up 12 plus the original 4, it's 16. So you have to add 6 more to the center atom. Okay. So again, let's count. Let's make sure we got this count right. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Okay. Now you're going to want to go back to your Chem 107 and you're going to say, hey, wait a minute, Mr. Fernandez, doesn't everything get an octet? I'm going to tell you, but remember, there's only 4 atoms that really need an octet. What are those 4? CNOF, right? CNOF isn't in here. So this central iodine atom will get an extra pair of electrons. And because it's a polyatomic ion, it would be put in brackets too. All right, formal charges for this would be 0, -1, and 0. Those would be the formal charges. All right, so we get the Lewis structure. Now what about the VSEPR sketch? All right, what's it going to look like?
Can you refresh my memory on the formal charges again?
Right, so a free iodine atom, just iodine by itself, is going to have a dot structure that looks like that, right? All right, this has 7 electrons. And then I would look at, say, this middle iodine atom. And when I look at the number of dots around this iodine atom, how many dots do I have around it? I've got 8, right? So I would take this down here, you know, it's got those 8, and I would say 7 minus those 8 equals -1. And that's where that formal charge comes from. So it's the group number 7A for iodine, minus the number of bonds plus the number of dots. Okay. So the way I was doing it was like 7 minus 2 bonds plus 6 dots, and that was -1. So it's almost like you're taking this minus that, you know. Okay. In Chem 107, I called it the valence match, but I didn't want to use formal charge yet because I feel like I'm not allowed to. I don't know. I'm allowed to, but the textbook tells me I'm not allowed because they don't mention it. So, you know, anyway. I'm not allowed to, so I'm not going to mention it. All right. Okay, so we have -1 here, and then these were 0 because there were 7 dots around that, right? So 7 dots around these guys. Okay, so we have, what's our steric number? So when I say what's our steric number, which atom am I referring to? I'm always talking about the central atom. It has to be a central atom because outer atoms don't have a shape around them, right? You know, so the steric number for that middle iodine is going to be how many bonds? 2 bonds plus how many lone pairs? We're doing it by pairs. Yeah, I've got 3 pairs, right? So I've got this bonded atom, and then I've got these 3 pairs. So don't confuse it with formal charge where I'm just counting the dots. In this case, I'm counting the bonds, the bonded atoms, right, for steric number. So I still have a steric number 5. My electron geometry is going to still be what? Trigonal bipyramid. Trigonal bippy. I don't know how I say that. But. And then what would be the molecular shape? So if you look at your chart there, under steric number 5, electron geometry, and you look at the one that has 3 lone pairs, and it tells you that the shape is going to be linear, right? So the shape will be linear. Okay, so let's go ahead and draw our generic bipyramid like we did that time. Okay. So I'm just throwing in any atom on the equatorial positions. When you take off atoms and replace them with lone pairs, where are you replacing them for a trigonal bipyramid? The equatorial, right? So what ends up happening is we take off this equatorial atom and then these two, and then we get a linear shape. So again, if you wanted to do the phantom lone pairs, so yes, we have lone pairs that are there, but really the shape is just this linear compound. Do I have to put the brackets around the VSEPR sketch? I don't, right? So that's also something that some people ask. So notice I'm always starting with the generic bipyramid shape, and I'm just taking off lone pairs where they're supposed to be taken, put on, right? I'm always taking off equatorial atoms first, replacing them with lone pairs. Real quick, quick question. What if I had taken, kept this atom on, and I put the lone pair over on one of these two? What would it look like? Right, I could have drawn that shape. What if I left it like that? Would that be correct? It would be correct. So if you drew this, if you wanted to draw this instead of that shape over there for SF4, okay, it would still be correct. Okay, it's just that now the lone pair is here instead. Okay, but it's still a viable shape. So that's what I'm saying, to try and memorize what a seesaw is going to look like is kind of a fool's errand. Okay, just stick with the generic trigonal bipyramid. And you can take off a lone pair off the equatorial wherever you want, okay, as long as it's equatorial. All right, so you just need to memorize 5 generic shapes, okay, on how to draw them. And it's those 5 in your table. That's all you got to know. What about, let's see, we've got one last one here, xenon tetrafluoride. Okay, what would the Lewis structure look like? Anyone venture to guess? Okay, so in the middle, and you got these fluorines on the outside. Okay, so I know I got 28 electrons from the fluorines, right, group 7, there's 4 of them. So 28 from here, plus another 8 from the xenon. So that's 36 total. Okay, so I've used up 32 here, so I got to add 4 more. And those last 4 electrons must go on the xenon. What's the steric number? it's 6, right, it's 4 bonded atoms plus 2 lone pairs on the xenon equals 6. So the electron geometry is a, well, that's the shape. All right, the electron geometry is a octahedron or octahedral. All right, the shape, molecular shape is a square pyramid. All right, how do we draw a square pyramid? And the question really should be, how do we draw an octahedron and then take atoms off to make the square pyramid? That's the question. Okay, so normally I would say, okay, here's a generic octahedron. How do we draw a generic octahedron? You've got it on your sheet. It's going to be one line up, one line down, a dash there, a dash here, a dash of salt here, a dash of fluorine here, a wedge of fluorine there. It's like food, you know? Or not. So that would be a full-on octahedron. Yeah.
Why would it be a square pyramid? Just 2 lone pairs.
It's not a square. Oh. Thank you. It's not a square pyramid. That's why. Good catch. It is a square plane. I still haven't gotten over the bipyramid yet, so sometimes I do that. You might do that too, just by accident, even if you know it. Yeah. Anyway, so it's a square plane, not a square pyramid. Okay, so how do we draw a square plane from this? Where do the lone pairs go? They go on the axial positions now. So now we're going to take off this axial position and that one, and there's our square plane. Why do they call it a square plane? Well, if I take a octahedral compound and I take off a lone pair from the axial, or I add lone pairs to the axial positions, got to take off the axial atoms, and what do you have? You got a planar molecule now, right? It's a plane, and it's kind of like a square, right? So it kind of makes a square. So moral of the story, don't memorize all the shapes in terms of how to draw them. Just memorize the 5 generic electron geometry shapes. That's all you really need to know how to draw. And then as long as you know where to take off atoms and replace with lone pairs for the trigonal bipyramid and octahedral shapes, or electron geometries, you're good to go. Okay, yeah?
I'm confused because don't you take off lone pairs for the core?
Only for trigonal bipyramids. Right. For electron geometries that are octahedral, you take off atoms from the axial positions and replace them with lone pairs. So again, if you wanted to add some lone pairs on here, here's a lone pair, here's a lone pair. Just to dig a little deeper, why do the lone pairs go on the axial positions for an octahedron? What's the whole goal of VSEPR again? It's to minimize repulsions between neighboring groups, right? Whether they're atoms or lone pairs. The lone pairs take up the most space, so it makes sense to have lone pairs opposite each other so they've got the most space. Right, so the reason why the lone pairs go on the axial positions is because you're maximizing the angle between those lone pairs, right? And the maximum angle you can have is 180. That's the maximum angle you can have. So what's the point? What's the whole point of VSEPR again? What is the goal of it? It's to minimize. Maybe etch that in word in your mind. Minimize repulsions between neighboring groups. Okay. What are groups? What am I talking about by groups? I'm talking about bonded atoms or lone pairs, right? How we calculate steric number. So the larger angles that we can have between other bonded atoms between each other, or the greater the angle we can have between the lone pairs, that helps us minimize these repulsions. And that's the whole point. I'll probably say it another 50 times. So. Questions? No? Are we waking up a little bit on this fine Saturday morning? Okay. What if we have a bigger molecule with multiple central atoms? Okay, so in this case, what we have to do is we have to have an assigned shape to each inner atom. Okay, so here's an example. Assign shapes to all the inner atoms in the structure below, then draw its VSEPR sketch. This takes a little bit of artistic talent, maybe. I don't know. Yes?
So what's the formula for this?
What is the formula for
So
it?
is it like C?
Right, so if you were to draw out a chemical formula, that's a good question because your lab manual was written to expect you to somehow know how to put together organic structures, which is, I think, a bit laughable, but you'll get it, but it takes time for that to happen. So, but if you were to just write out the chemical formula for this, it would be CH3 followed by CH2, 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 and then OH. And you could write it out like that. Right? That would be the chemical formula for that compound. Okay, if you really wanted to, now, you can still make sense of this in relation to that, I'm guessing. Now here's what would be impossible, right? What if they just combined all the carbons? C4, H, H10, O. Right, if you saw that, you wouldn't know that it's that structure.
It's like that on homework.
It was like this? Or was it like this?
Similar to that. No, it was, I believe it was like C2, H8, something else.
Yeah, but it wouldn't ask you to do a Lewis structure just based on this. There's too many possibilities. Because there's other ways I can rearrange those carbons. So if you can find that for me, I'll take a look at it. But if that's the case, I'll take that problem off. But I'm pretty sure I thought I avoided all those or possible situations. So anyway, but sometimes they'll give it to you like this, and actually this is the next thing we'll talk about right after this. So we have this formula, right, and it's that Lewis structure. Okay, what are the shapes of these? Man, this really hurts my arm. I gotta tell you. When we get to line structures, you're just gonna be like, thank you. There is a higher power. I'm telling you. When we get to line structures, and if just right after we talk about polarity, okay, you're gonna be like, man, why don't they just show this from the very beginning? So you draw this big old structure, right? How many central atoms do I have in this molecule? I've got 4 central carbons, but I also have a central oxygen, right? So these 5 atoms are all bonded around by other atoms.